Good morning. Today we're starting the second half of LeetCode 75, and I'm going to try something new. Instead of jumping right into coding and solving the problem, I've made a list for myself to make sure that I spend time checking the problem, the constraints, and the edge cases, really thinking about the problem, and then diagramming the problem using ExcaliDraw, and not just jump in and try to solve it. I think today's going to be a pretty easy one. I've obviously solved it in the past, so we'll try this solution out. So today is binary tree right side view. Given the root of a binary tree, imagine yourself standing on the right side of it and return the values of the nodes you see ordered from top to bottom. Okay, so yeah, this seems like a pretty simple problem, but I'm not going to jump in and solve it. I want to ask questions about it. So, in this example, they're all unique numbers. I wonder if that's always the case. These are unique, but they're not sequential the way example 1 was. The number of nodes in the tree is in the range 0 to 100, and the node value is negative 100 to 100. So it's not telling me exactly if the nodes are sequential. Well, they're not sequential. It's not telling me if they're unique. Nodes may not be unique. I doubt that'll be a problem, an issue in this problem, but it could be in another problem. And the output needs to be a list. Return the values of the nodes you see top to bottom. So it's not telling me what the output is, but it's showing me what is the output, assuming list. Any edge cases I can think of? There could be an edge case where it's all... Oh, you know what? It's going to be a little more complicated than I thought, because if this is 1, then 3, then 5 would be the next one. So edge cases, right side is shorter than left. But I'm already coming up with a solution for that. So let's take, this is a picture. So let's, go halfway with this guy. And then we're going to copy this over here so we can start messing with it. So in the easy case, all I have to do is travel down the right side of the list. And I need to have a list of my own set off to the side. So let's put this inside the class. We'll call it self.rightView. And so we'll go through 1, 3, 4. Okay. Now, so that means all I have to do is call node.rightSide, and each time I find a node, I append to self.rightView, then return. Now, the question is, let's do this again, and we'll get rid of one of these. Okay, so now we want a list. Background clear, red, letters, self.write view. And this time it's going to be 1, 3, and 5. Okay, so if I travel down the right side first, get every right side out of the way, then I go to the left. And each time I hit a right node, I'm going to check the length of self.write_view. So I head down here. So each time I hit a node, I'm going to check the length of self.write_view. I think I can just do that. It doesn't matter if it's a right node or not. Yeah. So I'll come down here. This is 1, which is greater than the length of self.write_view. So I'm going to go here. As in the count is 1, not the number is 1. So then I go to the next one. That's 2, which is greater than the length of self.write_view. So then we're going to put this guy here. Now I've ended, so I'm going to return. And then I get up to the top, I'll go down the left. Now, 2 is not greater than the length of self.write_view. So I don't do anything with it. Then I go down to 5. At 5, our count is up to 3 again. Our count is up to 3, which is greater than self.write_view. So we're going to add 5. And then we return up. Now if 5 was over here, coming off of 3, then it would miss this one, it would miss 4, bounce back and hit 5. If 5 was over here, it would miss this branch and hit 5. So as long as it's checking the right side first, it's always going to find the rightmost. And as long as it's only appending when the length is greater than the list, it'll work. Okay, so now I think I have a plan. So over here, we're going to do a recursive solution, and we're going to use a helper function. First, we're going to do self.write_view equals empty list. Then we're going to define, drill down, let's call it DFS. And then we're going to give it a node. Yeah. Node is tree node, optional tree node. And then it's going to return nothing. Our return value is held in right view. Okay. So So first we're going to check if tree node is there. If not node, return nothing. Okay. And then we're going to, I need an integer for depth. Yeah, let's call it depth is an int. Okay, so if depth greater than the length of self dot right view, return not return right view self dot right view dot append depth. No. Node dot val. Let's go with depth equals 0 for the first call, which means depth plus equals 1 before doing that. Okay, and then, so we've appended, now we have to call the right side. So dfs node dot right depth dfs node dot left depth, and then so we're done with that. We're going back. We want to depth I don't need to return depth because it starts at the current depth regardless. It gets added. So that's it, I think. Don't even need to return anything. So here I return self.rightView. And I think that's all there is to it. Test. Wrong answer. What did I do? Output is nothing. Self.rightView. It was never... Oh, I didn't even call the function. Okay. DFS root depth of 0. Run. There we go. Submit. And beat 73% with 97% memory. It's pretty good. Wonder what the super solution is. They used a deck instead of recursion. Interesting. I'm not sure that using a deck is actually faster in the worst case. I'm betting that 73% is just random, and if I applied a bunch of times, I might get a higher score. And considering that this also beats out everyone in memory, I think I'm pretty happy with my solution. Well, that was a lot of fun. Thanks for joining me.